Tonight, we're going to explore something that sounds simple, but reveals one of the most unsettling truths about the universe: darkness. You think you know what darkness is. You've experienced it when you turn off the lights at night, when you close your eyes, when you're in a room with no windows. But here's what most people don't realize. The darkness you've experienced on Earth is nothing compared to the true darkness of space. It's not just the absence of light. It's a darkness so complete, so absolute, that it challenges everything your brain evolved to handle. And by the end of tonight, you're going to understand exactly why space is darker than anything you can imagine, and why that darkness tells us something profound about the universe itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what you think darkness is. When you're inside your house at night with all the lights off, you probably think it's dark. Maybe you can barely see your hand in front of your face. The room feels pitch black. But here's the thing. It's not actually dark. Not even close. Your eyes are still receiving light. Light leaking in from street lamps outside, from the moon if it's up, from neighboring houses, from the distant glow of cities on the horizon. Your pupils dilate in response, expanding to let in as much light as possible. The rod cells in your retina adapt to the low light conditions. After about 20 minutes, your eyes reach their maximum sensitivity. You can detect incredibly faint sources. The glow of electronics, the subtle difference between the darkest shadows and slightly less dark areas. Your brain fills in details, constructs a mental image from minimal information. Even in what feels like complete darkness, you're never truly without light on Earth. The atmosphere itself scatters light from human civilization. Cities create a glow that extends for miles. Even in the most remote locations on Earth, far from any city, there's still light. The moon can cast shadows when it's full. Stars contribute thousands of photons to your retina. The Milky Way creates that faint band of light across the sky. There's airglow from atmospheric reactions, zodiacal light from dust in the solar system, light pollution scattered by the atmosphere from cities hundreds of miles away. On Earth, you're surrounded by light sources. You're at the bottom of an atmosphere that traps and scatters light. Even on the night side of our planet, the sun's light reflects off the moon, off other planets, off dust in space. You're never truly in darkness. Now, let's talk about space. When astronauts first travel beyond Earth's atmosphere, one of the most startling experiences they report is the darkness. Not the darkness of looking at space from Earth, where you see stars against a black background, but the darkness between those stars. The darkness that exists in the vast emptiness between everything. Bruce McCandless, the first astronaut to perform an untethered spacewalk, described looking away from Earth and the Sun during his historic spacewalk in 1984. He said the darkness was unlike anything he'd experienced. A complete void. A darkness so deep it felt almost physical. He couldn't see his own hand when he held it away from any reflected light. The darkness didn't just surround him. It penetrated everything. Other astronauts have described similar experiences. Looking out into space, away from any illuminated objects, into the deep void between stars, creates a psychological effect that's difficult to describe. Your brain expects to see something. It expects texture, variation, any kind of information, but there's nothing. Just pure, absolute darkness. This darkness exists because space is almost entirely empty. When we say empty, we mean empty in a way that's hard to comprehend. In the space between stars, there might be one atom per cubic centimeter. One single atom in a space the size of a sugar cube. On Earth, that same volume contains about 27 billion atoms. 27, followed by 18 zeros. The difference is incomprehensible. Space is a vacuum so extreme that we cannot recreate it in laboratories on Earth. Our best vacuum chambers, our most advanced technology, cannot approach the emptiness that exists naturally in space. And in that emptiness, there's nothing to reflect light, nothing to scatter light, nothing to create any illumination whatsoever. Light travels through space, yes. Photons cross the void between stars. But unless those photons hit something, unless they enter your eye or strike a surface, they're invisible. You can be surrounded by light, traveling in every direction, passing through the space you occupy, and you'll see nothing. You'll be in complete darkness. Because darkness isn't the absence of light sources. Darkness is the absence of light reaching your eyes. And in space, unless you're looking directly at a light source, like a star or a planet, no light reaches your eyes. Let's think about what this means practically. Imagine you're in a spacecraft, far from any star. You're in interstellar space, the region between star systems. The nearest stars are light years away, reduced to faint points, even through the largest telescopes. You look out the window, away from those distant stars. What do you see? Nothing. Not blackness in the way we normally understand it. Not the black of a painted wall or a dark room, but an absolute void. A darkness so complete that your brain has no reference for it. No variation in shade, no subtle differences in tone, no texture or depth. Just nothing. Your eyes, evolved over millions of years to detect even the faintest light, to find nothing to detect. The rods in your retina, capable of responding to single photons under ideal conditions, receive no signal. Your visual cortex, the part of your brain that processes sight, has no information to work with. In this darkness, you effectively have no vision at all. You might as well be blind. You could hold your hand directly in front of your face, touching your nose, and you wouldn't see it. You could wave it around, and there would be no visual indication of movement. The darkness is so complete that the concept of seeing becomes meaningless. This is the reality of most of space. The universe is not a place filled with stars and galaxies everywhere you look. The universe is mostly empty darkness, with occasional islands of light scattered across incomprehensible distances. Now, let's consider scale. When you look up at the night sky from Earth, even from a very dark location, you might see a few thousand stars with the naked eye, maybe 5,000, under absolutely ideal conditions. Those stars seem to fill the sky. The Milky Way appears as a band of light stretching across the heavens. It feels crowded, populated with stars. But that's an illusion created by distance and the limitations of human vision. Each of those stars you see is separated from its neighbors by vast distances. The nearest star to our Sun, Proxima Centauri, is approximately 4.24 light-years away. That's about 25 trillion miles, or 40 trillion kilometers. The average distance between stars in our region of the Milky Way is about 5 light-years. Now, imagine standing somewhere between those stars. Not near any of them, but halfway between. You'd be approximately 2.5 light-years from the nearest star in any direction. At that distance, our Sun would appear as a bright star, certainly, but just a point of light. It wouldn't illuminate anything around you. It wouldn't cast shadows. It would just be one bright point among other points. And in every other direction, darkness. Vast, empty darkness, stretching for trillions of miles before you encounter anything else. The psychological impact of this would be profound. Humans evolved on a planet where we're surrounded by surfaces, by objects, by light reflecting off things. Even at night, we have the ground beneath us, the sky above us with its stars and moon, the horizon in the distance. We have reference points, things to orient ourselves by. In the darkness of interstellar space, you'd have none of that. No up or down, no reference points beyond distant stars, no sense of scale or position. Just you, floating in absolute darkness, with only the faint points of distant stars providing any indication that a universe exists at all. Some astronauts who've spent time in space report feeling this isolation, even while still near Earth. Looking away from our planet into the void creates a sense of profound loneliness. Now imagine being light years from any planet, from any world with life, from any structure or object larger than a dust grain. The isolation would be total. The darkness would be absolute. But interstellar space, as dark as it is, isn't the darkest place in the universe. Let's go darker. Between galaxies, in the vast intergalactic void, darkness reaches a new level of absoluteness. Galaxies are separated by distances that make interstellar space seem crowded. The Milky Way and Andromeda, our nearest large galactic neighbor, are approximately 2.5 million light-years apart. That's about 15 quintillion miles. 15 followed by 18 zeros. Between these galaxies lies space that's even more empty than the space between stars. The density of matter in intergalactic space is about 1 atom per cubic meter. Not per cubic centimeter, like between stars. Per cubic meter. That's roughly 1 atom in a space the size of a large refrigerator. Imagine being in a spacecraft in the void between the Milky Way and Andromeda. You're roughly 1.25 million light-years from either galaxy. You look in one direction, and you see the Milky Way. Not as we see it from inside, not as a band of light across the sky, but as it appears from outside. A spiral galaxy, faint, distant, perhaps visible, but certainly not bright or detailed. You look in the other direction and see Andromeda, another faint spiral. And in every other direction, darkness. Pure, absolute darkness, extending for hundreds of thousands of light-years in every direction before you encounter anything else. The nearest other galaxies might be millions of light-years away, reduced to faint smudges even through powerful telescopes. In this darkness, you'd truly be alone in a way that's difficult to imagine. The stars of the Milky Way, our sun among them, would be invisible as individual points. They'd blend together into the faint, overall glow of the galaxy itself. Earth would be completely invisible, lost somewhere in that faint blur of light. Everything humanity has ever done, every person who's ever lived, every city and monument and achievement, all of it contained in one of those 2 faint smudges of light in an otherwise empty sky, and you'd be in the darkness between them. Now, let's talk about what causes this darkness. Why is space so dark? The answer seems obvious at first. Space is dark because there's nothing there to produce light. But that's only part of the answer. There's actually light everywhere in space. Light from stars, light from galaxies, light from quasars and other energetic objects. light from the cosmic microwave background radiation left over from the Big Bang. Space is full of light, traveling in every direction. So, why is it dark? Because light is only visible when it interacts with something. A photon traveling through space is invisible until it hits something. On Earth, you see light beams because they're illuminating dust particles in the air, or because they're scattering off air molecules. You see a flashlight beam because the light is reflecting off particles between you and the flashlight. In space, there are no dust particles, no air molecules, nothing for the light to reflect off or scatter from. The light passes through the void invisibly until it hits something solid. This is why you can't see beams of sunlight in space the way you can on Earth. The sun produces an enormous amount of light, obviously. But in the vacuum of space, that light is invisible until it strikes something. You can be in direct sunlight in space and look to the side, away from the sun, and see only darkness. The sunlight isn't illuminating anything around you because there's nothing to illuminate. This creates unusual situations. One side of your spacecraft might be in brilliant sunlight, heated to 250 degrees Fahrenheit or 120 degrees Celsius. The other side might be in complete darkness, cooling to minus 250 degrees Fahrenheit or minus 157 degrees Celsius. There's no atmosphere to distribute the heat, no air to scatter the light, just stark contrasts between illumination and absolute darkness. Astronauts working in space have described this experience. Sunlit surfaces are blindingly bright. Shadowed surfaces are completely invisible unless they have their own lighting. You can be holding a tool in your hand, and if it passes into shadow, it disappears completely from view. You know it's there. You can feel it, but you can't see it. It's vanished into the darkness. Let's consider another aspect of space's darkness. The night sky paradox, also known as Olber's paradox. If the universe is infinite and filled with stars, as people once believed, then every line of sight should eventually hit a star. The night sky should be completely bright, filled with starlight in every direction, as bright as the surface of an average star. Obviously, that's not what we see. The night sky is dark. Why? The answer relates to the expansion of the universe and its finite age. The universe is approximately 13.8 billion years old. Light travels at a finite speed, about 186,000 miles per second. This means we can only see light from objects less than 13.8 billion light-years away. Light from anything farther hasn't had time to reach us yet. So the observable universe has a horizon beyond which we cannot see. Additionally, the universe is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This expansion stretches the light from those galaxies, shifting it toward longer, redder wavelengths. For the most distant galaxies, the light is stretched so much that it moves out of the visible spectrum entirely, becoming infrared or even microwave radiation. These galaxies still exist, and their light is still reaching us, but we can't see it with our eyes. So, even though space contains countless galaxies, each with billions or trillions of stars, most of their light either hasn't reached us yet or has been stretched beyond visibility. The darkness of the night sky, the darkness of space itself, is partly a consequence of the universe having a finite age and expanding. If the universe were infinitely old and static, space would indeed be bright. But it's not. It's dark, profoundly dark. Now, let's talk about what this darkness means for us practically. Human eyes evolved on Earth under conditions where there's always some light. Even at night, even in the deepest caves, there are usually faint light sources. Bioluminescence from organisms, faint chemical reactions, radiation from rocks. Our eyes can detect incredibly faint light when given time to adapt. Under ideal conditions, a human eye can detect as few as 100 photons entering the pupil. Some studies suggest we might even be able to detect single photons under perfect conditions. That's remarkable sensitivity. But in space, in true darkness, there are no photons to detect. Zero. Your eyes can be as adapted as possible, as sensitive as possible, and they'll see nothing because there's nothing to see. This creates real challenges for space exploration. Spacecraft need artificial lighting for any work done in shadow. Without it, astronauts are effectively blind. The International Space Station, for example, has extensive external lighting for spacewalks. When astronauts work on the shadowed side of the station, they rely entirely on these lights. Without them, they couldn't see their hands, their tools, the station structure, anything. Future missions to more distant locations will face similar challenges. Asteroids, for example, are often very dark objects. Many asteroids reflect only 3 to 5% of the light that hits them. That makes them darker than coal, darker than asphalt. When spacecraft approach asteroids, especially on the side away from the Sun, the asteroids are almost invisible. They appear as black shapes against the black background of space. Only careful observation and computer processing can reveal their location and shape. For a human visiting an asteroid, the experience would be surreal. Standing on its surface on the sunlit side, you'd see the terrain around you illuminated by harsh sunlight. But looking into shadows would reveal absolute blackness. Craters, crevices, any feature not directly lit would be completely invisible. And if you were on the night side of the asteroid, away from the sun, you'd be in total darkness. Even with starlight from millions of stars, there wouldn't be enough illumination to see anything. You'd need artificial lighting for even the most basic tasks. This is true for most objects in space. Moons, asteroids, comets. All of them have day sides and night sides. And on their night sides, without artificial light, you're in absolute darkness. Let's go even darker. Inside objects. Inside asteroids, inside moons, inside planets. When you're inside a cave on Earth, it can be dark. If you go deep enough, far enough from any entrance, you reach a point where no light from outside reaches you. You're in complete darkness. But that's still not as dark as space for one reason. Your body produces light. Extremely faint light, but real light nonetheless. All living organisms produce bioluminescence to some degree. It's a byproduct of metabolic processes. Your body emits photons continuously, though far too few for you to see with your own eyes. Specialized cameras can detect this ultra-weak emission. It's measurable, real, scientifically documented. So, even in the darkest cave on Earth, there's a tiny amount of light present because you're there. In space, in the true void, even this biological light doesn't help. The darkness is so absolute that even if you're producing photons, there's nothing nearby to reflect them back to you. They travel out into the void and are gone. Now, imagine being inside a large asteroid or moon. Some asteroids are big enough to have significant internal cavities. Hollows created by ancient impacts or volcanic activity or other processes. If you were inside one of these cavities, you'd experience darkness, unlike anything possible on Earth. No light from outside can reach you. No biological processes create measurable illumination. No chemical reactions in the rock produce light. Nothing. The darkness would be total, absolute, perfect. Your eyes would strain to see anything at all, and find nothing. No vague shapes, no subtle variations in blackness, no distant glimmers, just pure void. This kind of darkness has psychological effects. Studies of people in extremely dark environments, like deep caves or isolation chambers, show that extended periods without any visual input can cause hallucinations. The brain, receiving no signal from the eyes, starts generating its own images. You might see patterns, shapes, colors, entire scenes, none of it real. Your visual cortex, evolved to process information, starts inventing information when none is available. People describe seeing stars that aren't there, geometric patterns, sometimes complex imagery. All of it created by the brain, trying to make sense of complete sensory deprivation. In space, in the absolute darkness between stars or inside an asteroid, you'd likely experience similar effects. Your brain would rebel against the lack of input. It would create phantom images, trying desperately to see something, anything, to maintain the illusion of sight. Now, let's consider the psychological impact of this darkness on a deeper level. Humans are visual creatures. Roughly 30% of our brain is dedicated to processing visual information, more than any other sense. We navigate the world primarily through sight. We recognize faces, read emotions, judge distances, identify threats, all through vision. Take that away, and we become disoriented. We lose our primary means of understanding our environment. On Earth, even blind individuals have other cues. Sound reflects off surfaces, giving information about room size and obstacles. Air currents indicate open spaces or barriers. Temperature variations suggest proximity to walls or objects. In space, in the void, these cues largely disappear. Sound doesn't travel through vacuum. There's no air to feel. Temperature can vary dramatically, but it doesn't tell you about proximity to objects because there are no nearby objects. You're left with only proprioception, your internal sense of your body's position. You know where your limbs are relative to each other, but you have no reference for where you are relative to anything else. The isolation would be profound. The darkness wouldn't just be visual. It would be a complete sensory deprivation, unlike anything humans have evolved to handle. Some astronauts and cosmonauts have reported feeling profound unease when working in deep shadow during spacewalks. A primal fear response that's difficult to rationalize away. Your instincts, developed over millions of years, tell you that complete darkness means danger. It means you're vulnerable to predators, to unseen hazards, to getting lost. Even though you know intellectually that you're safe, that you're tethered to the spacecraft, that you have lights and communication, the emotional response remains. The darkness feels threatening. This fear is deeply embedded in our psychology. Throughout human evolution, darkness was when predators hunted. Darkness was when you were most vulnerable. Darkness meant you couldn't see danger coming. Our ancestors who feared the dark who sought shelter and fire when night came, were more likely to survive than those who wandered carelessly in darkness. That fear is written into our genes. It's why children are afraid of the dark. It's why horror movies use darkness to create tension. It's why being in a dark place, even when you know it's safe, can make your heart race. The emotional response is automatic, bypassing rational thought. In space, this primal fear meets an environment more dark than anything our ancestors could have imagined. Not just the darkness of night when predators might lurk, but a complete, absolute void. A darkness where there are no predators, because there's nothing alive at all. A darkness where the danger isn't what might be hiding there, but the emptiness itself. The fact that there's nothing, that you're alone in a way so complete it defies description. Some astronauts describe a moment of existential crisis when they truly comprehend this. When they look out into the void and understand that they're seeing nothing because there is nothing, that the darkness goes on forever, in every direction. That Earth, their home, everyone they've ever known, is just a tiny lit speck in all that darkness. The feeling of insignificance can be overwhelming. Not just intellectually understanding that you're small in cosmic terms, but feeling it viscerally, emotionally, seeing the proof of it in the endless darkness surrounding you. Some find this liberating. If you're insignificant in cosmic terms, then your problems are too. The things you worry about, the stresses and anxieties of daily life, become trivial when viewed against the backdrop of infinite darkness. Others find it crushing. The sense that you don't matter, that humanity doesn't matter, that everything we've accomplished is happening on a barely visible speck in an uncaring void. Both responses are valid. Both are ways of processing the reality that the darkness reveals. That we're temporary, local, small. That the universe is vast, old, and indifferent to our existence. That darkness is the dominant feature of reality, and light is the rare exception. In future long-duration missions, this could be a real challenge. Crews traveling to Mars or beyond will spend months in space. They'll look out windows and see mostly darkness. The sun will be a bright point, yes, but beyond that, only the black void. Earth will shrink to a pale blue dot, then disappear entirely. The psychological impact of being surrounded by absolute darkness for months could be significant. Cabin fever, depression, anxiety, all possible responses to the isolation and sensory deprivation. Consider a mission to Mars. The journey takes approximately 6 to 9 months with current technology. That's half a year or more of traveling through space. For the first few weeks, astronauts can still see Earth, though it's shrinking rapidly. A blue marble, then a blue dot, then just another point of light among the stars. Mars is ahead, but for most of the journey, it's also just a point of light. A reddish dot that slowly, very slowly, grows brighter and larger. Everything else is darkness. The spacecraft becomes your entire world. The bright interior spaces, the equipment, your crewmates, the tasks that fill your days. But outside every window, darkness. Absolute, unchanging darkness, broken only by stars that never move, never change, just hang there in the void. Astronauts who've spent time on the ISS report that looking at Earth is psychologically important. Seeing your home planet, watching it pass beneath you, seeing weather patterns and cities and coastlines, provides a connection to home. It reminds you why you're there, what you're working to protect and represent. On a Mars mission, that connection is severed. Earth disappears. You can't see it anymore. Radio communication has a delay that increases to 20 minutes or more at maximum separation. You can't have a conversation. You can send messages and receive replies, but it's not the same as talking to someone. The isolation becomes profound. You're truly on your own, your small crew in a tiny spacecraft, surrounded by darkness that extends for millions of miles in every direction. The nearest help is months away. If something goes wrong, you have to solve it yourself. There's no calling for assistance, no quick rescue mission. You're alone in the dark. This is why mission planners spend so much effort on psychological support. Regular communication schedules with Earth, even with delays. Entertainment systems with movies, music, books. Windows designed to provide views, even if those views are mostly darkness. The ability to adjust interior lighting to create variety, to simulate different times of day. Anything to prevent the monotony and isolation from becoming unbearable. Some crew selection criteria specifically test for psychological resilience. Can candidates handle long periods of isolation? How do they respond to being cut off from normal social connections? Can they maintain morale when surrounded by darkness and danger? These aren't physical challenges. They're mental and emotional challenges. The darkness of space doesn't just affect your eyes. It affects your mind, your mood, your sense of connection to the rest of humanity. This is why spacecraft designs for long missions include careful attention to lighting, to visual variety, to creating an environment that feels less like floating in a void and more like being in a safe, contained space. Windows might be limited or covered to prevent crew from fixating on the darkness outside. Interior lighting might simulate day-night cycles to maintain circadian rhythms. Visual art, colors, anything to provide stimulation for the visual system. Let's consider what happens to light in the darkest regions of space. We've talked about the visible spectrum, the light we can see. But that's only a tiny fraction of the electromagnetic spectrum. Light exists in wavelengths from radio waves, which can be meters long, to gamma rays, which are shorter than the nucleus of an atom. Visible light, the rainbow of colors we perceive, spans wavelengths from about 700 nanometers for red to about 400 nanometers for violet. That's less than 1 octave on the electromagnetic spectrum, less than 1 doubling of wavelength. The full spectrum spans more than 60 octaves. We're seeing less than 2% of the light that exists. In the darkest regions of space, there's still light, but most of it is outside our visual range. Infrared radiation from distant galaxies, stretched by the expansion of space. Microwave radiation from the cosmic microwave background, the afterglow of the Big Bang. Radio waves from pulsars, quasars, and other energetic objects. All of this is light, electromagnetic radiation, but invisible to us. To our eyes, these regions appear absolutely dark. But to instruments sensitive to these wavelengths, they're full of information. The James Webb Space Telescope, for example, observes primarily in infrared. It can see galaxies that are completely invisible to optical telescopes because their light has been stretched into infrared by cosmic expansion. Radio telescopes detect signals from objects billions of light years away, signals that pass through dust and gas that would block visible light. So, the darkness we perceive is partly a limitation of our biology. We evolved to see the wavelengths of light that our sun produces most strongly, the wavelengths that pass through Earth's atmosphere most easily. It's the light that was most useful for survival on Earth. But in space, that's a narrow slice of the information available. If we could see in radio waves or infrared or X-rays, space would look very different. Not empty darkness, but filled with structure and light and activity. But we can't. To our eyes, space remains dark. There's another layer to understanding darkness that we should explore. At the quantum level, darkness is not truly empty. Quantum mechanics tells us that even a perfect vacuum isn't truly empty. It's filled with quantum fluctuations, virtual particles that pop into and out of existence. These fluctuations occur everywhere, constantly, even in the darkest regions of space. Particle-antiparticle pairs appear spontaneously, exist for an infinitesimally brief moment, then annihilate each other. This happens throughout space, even in regions we perceive as absolute darkness. The energy associated with these fluctuations is called vacuum energy or zero-point energy. It might be connected to dark energy, the mysterious force driving the universe's accelerated expansion. So, in a sense, the darkness is not empty at all. It's seething with quantum activity that we simply cannot observe directly. Our instruments, our senses, our entire perception of reality operates at scales much larger than quantum fluctuations. We see the darkness as empty because we cannot perceive what's happening at the quantum level. This raises philosophical questions about the nature of darkness itself. Is darkness truly the absence of light? Or is it simply our inability to perceive what's there? If space is filled with quantum fluctuations, with dark matter, with dark energy, with neutrinos streaming through every point, is it really empty? Or is it full of things we cannot detect, and our perception of darkness is just a limitation of our senses? These aren't just academic questions. They affect how we think about space, about reality, about what it means for something to exist. If a particle exists for only a fraction of a second before annihilating, did it really exist? If dark matter passes through you constantly, but you can never feel it or see it, is it really there? Physics says yes. The mathematics predicts these phenomena, and indirect evidence confirms them. But human experience says otherwise. To us, if we can't see it or feel it or detect it, it might as well not exist. The darkness appears empty because everything in it is invisible to us. This creates a disconnect between our subjective experience and physical reality. We look at space and see darkness, emptiness, void. But instruments detect photons at various wavelengths, cosmic rays, neutrinos, gravitational waves, all streaming through what appears to be empty space. Space is not empty in any meaningful physical sense. It's just dark to our eyes. There's also the matter of perception itself. What you see as darkness is actually a signal from your brain. When photons hit your retina, they trigger chemical reactions in rod and cone cells. These cells send electrical signals to your brain through the optic nerve. Your visual cortex processes these signals and creates the experience of seeing. But when no photons hit your retina, when you're in complete darkness, your visual cortex doesn't receive input. And yet, you still experience something. You experience darkness. That darkness is not external. It's a creation of your brain, a representation of the absence of input. Some researchers have studied what happens to the visual cortex during prolonged darkness. In experiments where people spent days in completely dark environments, brain scans showed that the visual cortex didn't become inactive. Instead, it started responding to other inputs. Sound began to activate visual areas. Touch began to activate visual areas. The brain, denied visual input, recruited those processing regions for other purposes. This is called cross-modal plasticity, and it happens relatively quickly. Within days of complete darkness, your brain begins reorganizing itself. In space, astronauts don't experience prolonged complete darkness because spacecraft have interior lighting. But if someone did spend extended periods in the absolute darkness of space, their brain would likely undergo similar changes. The visual cortex would repurpose itself. Returning to normal lighting conditions might require readaptation. This adds another dimension to understanding darkness. It's not just an external condition. It's also a neurological state, an experience created by the absence of sensory input and the brain's response to that absence. The darkness of space, then, is both real and subjective. Real in that photons are not reaching your eyes. Subjective in that your experience of that darkness is created by your brain. Another person might experience the same darkness differently. Some people are more sensitive to low light levels. Some can detect patterns in darkness that others cannot. Some find darkness peaceful, others find it threatening. The physical reality of space's darkness is objective. The experience of that darkness is deeply personal. Now, let's talk about the darkest places we know of in the universe. Black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. The event horizon is the boundary of no return. Cross it, and you're pulled inexorably toward the singularity at the center. Light trying to escape from beyond the event horizon curves back inward, trapped by the extreme gravity. This makes black holes truly, perfectly black. They don't emit light. They don't reflect light. They absorb everything that comes near them. To look at a black hole is to see literally nothing, a circular region of absolute darkness against the background of space. We've recently captured images of black holes, or more accurately, images of the material around black holes. The Event Horizon Telescope collaboration produced images of the supermassive black holes at the centers of the M87 galaxy and our own Milky Way. These images show a bright ring of hot material orbiting the black hole, with a dark center where the black hole itself exists. That dark center is the black hole's shadow, the region where light is either absorbed or bent away from our line of sight. It's darker than anything else in the image because it's an actual void, a place where light goes to disappear. If you could somehow survive near a black hole, the experience would be surreal. Looking toward the black hole, you'd see a circular region of absolute darkness, a hole in space where nothing exists, not even the distant stars that should be behind it. Those stars would be distorted around the edges, their light bent by the black hole's gravity, creating a ring of distorted light surrounding the void. But at the center, nothing. Pure, absolute darkness. The ultimate dark. And if you were falling into a black hole, as you crossed the event horizon, you'd enter a darkness beyond anything else in the universe. No light from outside could reach you because it would be bent away by gravity. You'd be inside a region of space-time that's causally disconnected from the rest of the universe. The darkness would be total and final. Of course, you wouldn't survive this. Tidal forces near a black hole would tear apart any normal matter long before you crossed the horizon. But hypothetically, if you could somehow endure the forces, the darkness you'd experience would be absolute. No light from any source, anywhere in the universe, could reach you. You'd be in a darkness more complete than anything we can conceive. Let's talk about the practical realities of living with space's darkness. Humans have only spent significant time in space near Earth, where the sun is still bright and planets and stars provide visual reference points. The International Space Station orbits at about 250 miles altitude. At that distance, Earth fills much of the view from the windows. The sun provides the same illumination it does on Earth's surface, actually slightly stronger because there's no atmosphere to absorb or scatter the light. Crew members experience 16 sunrises and sunsets per day as the station orbits Earth. They're never in darkness for more than 45 minutes at a time. Even when the station is on Earth's night side, city lights below provide substantial illumination. The station itself has internal lighting that mimics day-night cycles. So, astronauts on the ISS don't really experience the true darkness of space. But future missions will. The Artemis program plans to return humans to the moon. On the lunar surface, the darkness will be more intense. The moon has no atmosphere, so there's no twilight, no gradual transition from day to night. When the sun sets, darkness is immediate and absolute. The only illumination comes from Earth, hanging in the sky, and from stars. Earth light is substantial, much brighter than moonlight on Earth, because Earth is larger and more reflective than the moon. But it's still not bright enough for detailed work without artificial light. Lunar nights last about 14 Earth days. During that time, any location on the moon is in continuous darkness except for Earthlight and starlight. Astronauts will need to rely entirely on artificial lighting for activities during lunar night. Bases will need extensive external lighting systems. Rovers will need powerful headlights. Without them, navigation would be impossible. Mars presents similar challenges, though slightly less extreme. Mars has an atmosphere, thin but present, which creates some twilight. Sunlight on Mars is weaker than on Earth, because Mars is farther from the Sun, about 43% of Earth's solar illumination. But Mars has two tiny moons, Phobos and Deimos, which provide minimal light at night. Mostly, Martian nights are dark. Astronauts on Mars will need artificial lighting for nighttime activities, just as lunar astronauts will. As we venture farther from the Sun, the challenges increase. Jupiter receives only about 4% of the sunlight Earth does. Saturn receives only about 1%. At these distances, the Sun is still the brightest object in the sky by far, but it doesn't provide the same level of illumination. On Jupiter's moons, for example, the Sun would appear as a very bright star, bright enough to cast faint shadows, but not bright enough for comfortable human vision without artificial supplementation. Jupiter itself would provide substantial light when visible, reflecting sunlight onto its moons. But when Jupiter is below the horizon, or when you're on the far side of a moon, darkness would be deep. On Titan, Saturn's largest moon, the situation is different. Titan has a thick atmosphere, thicker than Earth's, which scatters sunlight. This creates a permanent twilight condition on the surface. Even at noon, Titan receives only about 1% of the sunlight that Earth does, and the atmosphere scatters it into a diffuse glow. Everything would be dimly lit, like being outdoors on Earth an hour after sunset. You could see, but not well. Details would be hard to make out. Colors would be muted. Artificial lighting would be essential for any precision work. Moving beyond Saturn to Uranus, Neptune, and into the Kuiper Belt, the Sun becomes just another bright star. Uranus receives about 0.27% of Earth's sunlight. Neptune receives only 0.11%. At these distances, the Sun is roughly 200 times brighter than the full moon appears from Earth. That sounds bright, but it's not enough for human activities without artificial light. You could navigate by sunlight in an emergency, maybe, but any detailed work would require lights. And in the darkness between illuminated areas, the void would be profound. Now, let's consider the future of human expansion into space, given these darkness challenges. If we establish permanent settlements on the Moon, Mars, or asteroid bases, dealing with darkness will be a constant concern. Habitats will need to be designed with this in mind. External lighting for safety and navigation. Internal lighting that provides full spectrum illumination to maintain human health. Psychological considerations to prevent the stress of long periods surrounded by darkness. Some designs propose building underground habitats, taking advantage of natural protection from radiation and temperature extremes. But this would mean no windows, no natural light at all. Residents would be entirely dependent on artificial lighting. This could have long-term psychological effects. Humans need visual variety, connection to external environments, a sense of place. Living in an underground facility on an asteroid or moon, surrounded by darkness when you venture outside, could be psychologically challenging. Other designs propose surface habitats with large windows, allowing views of the surrounding landscape. But this means looking out at mostly barren, dark terrain under a black sky. Without an atmosphere to scatter light, the contrast between illuminated and shadowed areas would be extreme. The sky would always be black, filled with stars, but providing no ambient light. This isn't necessarily bad, but it would be profoundly different from Earth. Some people might find it beautiful, inspiring even. The clarity of the stars, without atmospheric interference, would be stunning. The Milky Way would be visible in incredible detail. Other galaxies, nebulae, all the wonders of the cosmos would be on display. But for others, the constant darkness of the sky, the harsh shadows, the absence of blue skies and clouds, and all the familiar features of Earth's sky might be oppressive. We don't know how humans will adapt to these conditions long term. Will children born on the Moon or Mars who never experience Earth's sky find the darkness normal? Or will there be some fundamental human need for the kind of visual environment we evolved in? These are questions we'll only answer through experience. Let's talk about what the darkness of space teaches us about the universe. Space is dark because it's mostly empty. The universe is not a crowded place. It's vast, with matter concentrated in small regions like stars and planets, separated by enormous voids. This emptiness is fundamental to how the universe works. If space were not mostly empty, if it were filled with matter, gravity would cause everything to collapse together. Stars and galaxies exist in their current forms, precisely because they're separated by vast distances. The darkness between them is not a bug in the design of the universe. It's a feature. It's what allows structure to exist. The darkness also tells us about the age and expansion of the universe. The night sky is dark because the universe is expanding and has a finite age. If the universe were infinitely old and static, the night sky would be bright. Every line of sight would eventually hit a star. The fact that we see darkness instead confirms that the universe has a history, a beginning, and is evolving. The cosmic microwave background radiation, the afterglow of the Big Bang, fills all of space. It's light that's been traveling for 13.8 billion years, stretched by the expansion of space into microwave wavelengths. If we could see in microwaves, the sky would glow uniformly in every direction. But we can't see microwaves. To us, that light is invisible. The sky remains dark. This is a reminder that our perception is limited. We see a narrow slice of reality, the wavelengths of light our eyes evolved to detect. The universe contains far more information than we can directly perceive. Instruments extend our senses, allowing us to detect what our biology cannot. But even with all our technology, we're still sampling only a fraction of what exists. Dark matter, which makes up about 27% of the universe's total mass energy content, is completely invisible. It doesn't emit, absorb, or reflect light at any wavelength. We know it exists because of its gravitational effects, but we can't see it. The universe contains vast amounts of matter that contributes to its darkness by being inherently invisible. Dark energy, making up about 68% of the universe, is even more mysterious. It's driving the accelerated expansion of space, pushing galaxies apart. But we don't know what it is. It doesn't interact with light in any way we can detect. So roughly 95% of the universe's content is invisible to us. The darkness we see when we look at space is more profound than just the absence of light. It's the presence of things we cannot see, cannot detect directly, can only infer from their effects on the small fraction of the universe that is visible. Now, let's consider what happens to light itself over cosmic timescales. Light travels at a finite speed. This means when we look at distant objects, we're seeing them as they were in the past. The farther away something is, the farther back in time we're seeing. The Andromeda Galaxy, 2.5 million light-years away, appears to us as it was 2.5 million years ago. If it exploded tomorrow, we wouldn't know for 2.5 million years. The most distant galaxies we can observe are over 13 billion light-years away. We're seeing them as they appeared only a few 100 million years after the Big Bang. These galaxies are actually much farther away now, because the space between us and them has been expanding for 13 billion years. But the light we see from them began its journey long ago, when the universe was young. This means much of the light in the universe is still traveling, hasn't reached us yet. There are galaxies so distant that their light won't reach us for billions more years. And because the universe is expanding, accelerating in its expansion, there are galaxies whose light will never reach us. They're moving away faster than light can travel toward us. Not because they're moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. These galaxies are beyond our cosmic horizon. They contribute to the darkness because we cannot see them, can never see them, will never receive any light or information from them. In the far future, as the expansion continues, more and more galaxies will cross beyond our horizon. The observable universe will shrink. Distant galaxies will fade from view, their light redshifted into invisibility. Eventually, in trillions of years, galaxies beyond our local group will have disappeared. The darkness will deepen. Beings living in that far future will look out and see far fewer galaxies than we see today. They'll inhabit a darker universe. If they develop science and try to understand the cosmos, they'll be missing information that we have access to now. They might not even realize the universe is expanding because there will be nothing distant enough to observe the expansion. This is a sobering thought. Our position in time, right now, gives us a particular view of the universe. A different view than the past, a different view than the future. The darkness we see today is specific to our era. It could be darker. It will be darker. Let's think about this more deeply. In the very early universe, shortly after the Big Bang, there was no darkness at all. The universe was filled with a hot, dense plasma that glowed intensely. Every point in space was radiating light. There were no stars yet, no galaxies, just this primordial glow. As the universe expanded, this plasma cooled. Eventually, about 380,000 years after the Big Bang, it cooled enough for atoms to form. Electrons and protons combined into hydrogen and helium. Light that had been scattered constantly by free electrons could finally travel freely. This moment is called recombination, and it's when the cosmic microwave background was emitted. After recombination, the universe entered what's called the Dark Ages. There were no stars yet. The glowing plasma had cooled into neutral gas. The cosmic microwave background was still bright, but it was cooling and redshifting as the universe expanded. For hundreds of millions of years, the universe was truly dark, darker than it is now. No stars, no galaxies, no quasars. Just expanding clouds of hydrogen and helium gas, gravitationally collapsing in some regions, but not yet dense enough to ignite fusion. This was the darkest period in cosmic history. A universe filled with matter and energy, but producing no light. Then, gradually, the first stars formed. About 200 million years after the Big Bang, the first generation of stars ignited. These were massive stars, hundreds of times more massive than our Sun. They burned hot and fast, lived for only a few million years, then exploded as supernovas. Their light began to illuminate the darkness. Their explosions seeded space with heavy elements, carbon and oxygen and iron, elements that would later form planets and, eventually, life. Over billions of years, more stars formed. Galaxies assembled from smaller structures merging together. The universe became brighter. Not uniformly bright, but with concentrated regions of light surrounded by vast, dark voids. This is the universe we inhabit now. An era when stars are numerous, when galaxies fill the sky, when the darkness between them is profound, but the lights themselves are brilliant. But this era won't last forever. Star formation peaked about 10 billion years ago. It's been declining since then. We live in a universe that's already past its peak of light production. The future will be darker. Stars will continue to form for trillions of years, but at ever-decreasing rates. Eventually, all the available gas will be consumed or expelled from galaxies. No new stars will form. The existing stars will age and die. The most massive stars will explode or collapse into black holes. Medium-sized stars like our Sun will become white dwarfs, then gradually cool into black dwarfs. Small stars will burn for trillions of years, but even they will eventually exhaust their fuel. In about 100 trillion years, the last star in the universe will burn out. After that, the universe will be darker than it is now, much darker. No new stars forming, no existing stars burning. Just the remnants. Black holes, neutron stars, white dwarfs and black dwarfs, planets orbiting dead stars, asteroids and comets. All cold, all dark. The only light will come from occasional collisions. When a planet falls into a black hole, it will release a brief flash of radiation. When two white dwarfs collide, they might explode in a supernova, creating a brief moment of light. But these events will become rarer and rarer. The universe will sink into a darkness deeper than anything we see today. And still, the expansion will continue. The remaining structures, the black holes and dead stars, will drift farther apart. Eventually, even black holes will evaporate. Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly faint for large black holes. A black hole the mass of our Sun would take about 10 to the 67 years to evaporate. That's 1 followed by 67 zeros. A number so large it's meaningless in any practical sense. But given enough time, even supermassive black holes will eventually evaporate. After about 10 to the 100 years, all black holes will have evaporated. The universe will contain only photons, neutrinos, and other fundamental particles, all spread across space that's expanded to unimaginable size. The temperature will be effectively zero. The darkness will be absolute and eternal. This is the heat death of the universe, the final state predicted by thermodynamics. Maximum entropy, maximum disorder, no energy gradients to drive any process. Nothing happening anywhere. Just darkness, cold, and stillness forever. It's a bleak vision, perhaps. But it's also incomprehensibly far in the future. We're living in the bright era of the universe. An era when stars shine, when galaxies are visible, when life can exist. This era will last for many trillions of years more. Long enough for any civilization that survives to achieve things we can barely imagine. But eventually, the darkness wins. Not through any malevolent force, but simply through the inexorable march of physics. The expansion of space, the second law of thermodynamics, the limits of energy and matter. The universe began in light, passed through darkness, entered an era of light again, and will eventually return to eternal darkness. We're fortunate to exist during the bright era, to see stars, to witness galaxies, to observe the cosmos in its glory. Future generations, if they exist in that far future, will inherit a much darker universe. And they might look back at our era, at the images and data we've collected, and marvel at how bright the universe once was. Let's talk about artificial light in space and how it changes the darkness. Spacecraft and space stations use LED lights for most applications now. LEDs are efficient, long-lasting, and produce minimal heat compared to older lighting technologies. The International Space Station uses hundreds of LEDs throughout its modules, providing illumination for work and living areas. These lights can be adjusted in color and intensity to mimic natural day-night cycles, helping astronauts maintain circadian rhythms. But even with all these lights, looking out a window from the ISS into the darkness beyond is a stark experience. The interior is brightly lit, but that just makes the darkness outside seem more absolute by contrast. When astronauts perform spacewalks, they wear helmets with lights mounted on them. These lights illuminate the immediate work area, creating a bubble of visibility in the surrounding darkness. Beyond that bubble, darkness. Tools that float away into shadow disappear instantly. Dropped objects are lost forever, vanishing into the void. This is why everything on a spacewalk is tethered. Not just because of the risk of floating away, though that's real, but because losing track of something in the darkness is so easy. Future spacecraft designed for deep space missions will need even more sophisticated lighting. External lights for inspection and maintenance. Interior lights that can simulate natural illumination conditions. Emergency lights that function even if main power fails. All of this adds complexity, weight, and power requirements. But it's essential because humans cannot function in the absolute darkness that exists naturally in space. Some proposals for interstellar spacecraft imagine enormous vessels, perhaps miles long, with interior spaces that mimic Earth's environment. Artificial skies that project images of clouds and blue sky. Artificial sunlight that follows a day-night cycle. Parks and open spaces where crew can experience something resembling outdoors. All of this to combat the psychological impact of being surrounded by the darkness of interstellar space for decades or centuries. These designs recognize that humans need more than just survival. We need psychological comfort, visual stimulation, a sense of normalcy. Without these, the darkness outside, the knowledge that you're in a tiny bubble of light, surrounded by an infinite void, could be overwhelming. Now, let's consider what the darkness means for the search for extraterrestrial life. If intelligent civilizations exist elsewhere in the universe, we might expect to see evidence of their existence. Cities would produce light pollution. Large-scale engineering projects might reflect or emit detectable light. Communication signals would propagate through space at the speed of light. But we see none of this. The darkness is unbroken by any obvious signs of other civilizations. This is part of the Fermi paradox. If life is common, if intelligent civilizations arise regularly, where are they? Why don't we see evidence of them in all the darkness? Maybe we're alone. Maybe intelligent life is extraordinarily rare. Maybe we're the first, or among the first in our galaxy. Or maybe other civilizations exist, but are too far away for us to detect. Light from their worlds, if they're thousands of light years distant, might not have reached us yet. Or if it has, it might be too faint to distinguish from natural sources. A planet with cities, even a planet entirely covered in cities, would be incredibly faint when viewed from light years away. The light from its star would overwhelm any light from the planet itself. We're developing techniques to detect exoplanets, planets orbiting other stars. We've found thousands of them. But detecting signs of life, much less intelligent life, remains beyond our current capabilities. We can analyze the atmospheres of some nearby exoplanets, looking for gases that might indicate biological activity. But we can't see surface features. We can't detect artificial lights or radio signals unless they're aimed at us or are extraordinarily powerful. The darkness of space makes it easy for civilizations to remain hidden, even if they're broadcasting their presence. Distance and the vastness of space swallow the signals. Maybe the galaxy is full of civilizations, but they're all islands of light in the darkness, unable to see each other, unaware of each other's existence. Or maybe we truly are alone, the only minds contemplating the darkness, the only eyes seeing the stars. That would make the darkness even more profound. A universe full of potential, full of structure and complexity, but empty of other awareness. Only us, looking out from our small planet, trying to understand the void. Let's return to the human experience of this darkness. What does it mean for us personally? For most of human history, the night sky was a constant presence. Before electric lights, before cities, the stars were visible every clear night. Ancient peoples used them for navigation, for timekeeping, for mythology. The darkness of night was familiar, but it was a darkness filled with stars. Now, most humans live in cities where light pollution obscures the stars. You might see a few dozen stars from a typical urban location. The Milky Way is invisible. The true darkness of the night sky is hidden by the glow of streetlights and buildings. We've created our own artificial brightness that blinds us to the natural darkness above. This has consequences. Studies show that light pollution affects human health, disrupting circadian rhythms and sleep patterns. It affects wildlife, particularly nocturnal animals and migrating birds. And it separates us from the night sky, from the direct experience of seeing the cosmos. Let's examine this more closely, because it reveals something important about our relationship with darkness. For most of human history, night meant darkness. Real darkness, broken only by fire and later by candles or oil lamps. People's activity naturally followed the sun's cycle. Waking at dawn, working during daylight, resting after sunset. The invention of artificial lighting changed everything. First, gas lamps, then electric lights. Suddenly, we could extend our activities into the night. Work didn't have to stop when the sun set. Cities could operate 24 hours a day. This brought enormous economic and social benefits. But it also severed our connection to natural darkness. Today, about 80% of the world's population lives under light-polluted skies. In the United States and Europe, that number exceeds 99%. Almost no one in these regions experiences true natural darkness. The glow from cities spreads for hundreds of miles. Even rural areas have artificial lights, street lamps, house lights, vehicle lights. All of this contributes to a background glow that obscures the stars. From major cities, you might see only a few dozen of the brightest stars. The constellations are hard to make out. Planets are visible, but barely. The Milky Way, that band of light from billions of stars in our galaxy, is completely invisible. Many children growing up in cities today will never see the Milky Way unless they deliberately travel to a dark sky location. They don't know what they're missing. They think the night sky is supposed to look like what they see from the city. A few bright stars, maybe a planet or two, but mostly just empty blackness. This ignorance of the true night sky affects how we think about space. If you've never seen thousands of stars filling the sky, never seen the Milky Way stretching across the heavens, never watched meteors streak through the atmosphere, or caught a glimpse of a satellite passing overhead, then space seems abstract. It's something in textbooks and documentaries, not something you experience directly. But if you have seen a truly dark sky, if you've experienced the majesty of the cosmos displayed above you, then space becomes real. It becomes something you understand in your bones, not just in your mind. The darkness of space is connected to the darkness of Earth's night sky. Both are natural states that we've lost connection with through artificial light. Some people are fighting back against light pollution. Dark sky preserves have been established in various locations around the world. These are areas where artificial lighting is strictly controlled, where the natural darkness is protected. Visiting one of these preserves is like stepping back in time to when humans could see the true night sky. Thousands of stars visible, the Milky Way clearly defined, planets standing out brilliantly, satellites and meteors regularly visible. The International Space Station passing overhead, bright enough to cast a faint shadow. It's a transformative experience for many people. Seeing the cosmos like this changes your perspective. You realize how much we've lost in exchange for convenience and safety. You understand that darkness isn't just the absence of light. It's its own thing, valuable and important. There's also a health aspect to this. Humans evolved with clear day-night cycles. Bright light during the day, darkness at night. Our circadian rhythms, the internal biological clocks that regulate sleep and many other functions, are tuned to this pattern. Exposure to artificial light at night disrupts these rhythms. Your brain interprets the light as indicating it's still daytime, suppressing the production of melatonin, a hormone that promotes sleep. This can lead to insomnia, poor sleep quality, and over time, increased risk of various health problems. Depression, obesity, diabetes, even some cancers have been linked to circadian rhythm disruption. The darkness of night isn't just aesthetically valuable. It's biologically necessary for human health. By flooding our environment with artificial light, we're fighting against millions of years of evolution. Astronauts in space experience similar issues. On the ISS, crew members experience 16 sunrises and sunsets per day as the station orbits Earth. This rapid cycling would completely disrupt normal circadian rhythms if not managed. So the station uses artificial lighting programmed to follow a 24-hour cycle. Bright lights during scheduled day periods, dimmer lights during night periods. Crew members also wear sleep masks and use other techniques to maintain normal sleep patterns. Even with these measures, many astronauts report sleep problems. The unusual light conditions, combined with other factors like microgravity and the stress of spaceflight, make it difficult to get quality rest. On future long-duration missions, maintaining proper circadian rhythms will be critical for crew health and performance. This means carefully designed lighting systems that provide both the right intensity and the right spectrum of light. Blue-enriched light during the day to promote alertness. Warmer, dimmer light in the evening to prepare for sleep. Complete darkness during sleep periods, or as close to it as safety allows. These same principles will apply to space habitats and settlements. People living on the Moon or Mars will need lighting that compensates for the unusual day-night cycles. A lunar day is 29.5 Earth days. 2 weeks of continuous sunlight, 2 weeks of continuous darkness. No human could function on that cycle. Habitats will need to create artificial day-night cycles independent of the external environment. Mars has a day length close to Earth's, about 24 hours and 39 minutes. But the sunlight is weaker, about 43% of Earth's intensity. Habitats might need to supplement natural sunlight with artificial lighting to provide enough brightness for comfortable human vision and healthy circadian rhythms. All of this means that future space-based humans will live in carefully controlled light environments, not experiencing the natural darkness of space any more than we on Earth experience natural darkness due to light pollution. We'll be surrounded by artificial light, shielded from the true darkness beyond our habitats. In a sense, We're already practicing for this. Our cities are bubbles of light in the night, much like space habitats will be bubbles of light in the cosmic darkness. We've already adapted to living in artificial light environments. Extending that to space is just a matter of degree, not a fundamental change. But it does mean we're losing something. The experience of natural darkness, whether on Earth or in space, is becoming increasingly rare. And with it, we're losing a direct connection to the cosmos, to the reality of our existence in a dark universe. Many people grow up never seeing the Milky Way, never experiencing the sight of thousands of stars filling the sky. They don't know what they're missing because they've never experienced it. But if you travel to a truly dark location, far from cities, on a clear night, the experience is profound. The sky comes alive with stars. The Milky Way is clearly visible, a band of light crossing the heavens. You can see nebulae with the naked eye. The Andromeda Galaxy appears as a faint smudge. Satellites and meteors streak across your field of view. It's a reminder of what the night sky really looks like when we're not drowning it in artificial light. And even that, as beautiful as it is not the true darkness of space. From Earth, even from the darkest location, you're still looking through an atmosphere. You're still seeing scattered light, airglow, zodiacal light. You're still on a planet orbiting a star in a galaxy. The darkness between stars, between galaxies, the true void, remains beyond your direct experience. Only astronauts have seen it, and their descriptions consistently emphasize how different it is from any darkness on Earth. Now, let's think about what comes next. As we expand into space, as more humans live and work beyond Earth, the darkness will become a familiar part of life. Children born on the Moon or Mars will grow up with black skies. They'll never see Earth's blue sky except in videos and images. They'll never experience the way Earth's atmosphere diffuses sunlight, creating the brightness and color we take for granted. Will they miss it? Will there be a longing for the kind of skies their parents or grandparents describe? Or will they adapt, finding beauty in the stark contrast of bright sun and black sky? It's possible that future generations will prefer the clarity of space. No atmosphere means no weather to obscure the view. Stars never twinkle in space, they're steady points of light. The sun's light is harsh but pure, unfiltered by air. Some might find this appealing, honest even. The universe as it really is, not softened or obscured by atmospheric effects. Others might feel the loss keenly. The absence of sunsets, of clouds, of the gentle blue of a daytime sky, of rain and wind, and all the dynamic features of Earth's atmosphere. Space is beautiful, but it's a different kind of beauty. Stark, unforgiving, absolute. And always, always, there's the darkness. The black sky that never changes, never lightens with dawn, never glows with twilight. Just black, filled with stars, but fundamentally, eternally black. Living with this will require adaptation. Not just technological adaptation, but psychological and cultural adaptation. Humans are remarkably flexible. We've lived in deserts, in Arctic regions, in jungles, on mountains, anywhere on Earth that can support life. We've adapted our cultures, our technologies, our very identities to fit the places we inhabit. Space will be no different. We'll adapt. We'll create new cultures shaped by the environment of space. New aesthetics, new values, new ways of thinking about light and darkness and the universe. And maybe, in time, the darkness won't seem terrifying anymore. Maybe it will just be normal. The way things are. The natural state of the universe. Think about how human cultures have adapted to extreme environments on Earth. The Inuit people of the Arctic experience polar night, periods when the sun doesn't rise for weeks or months. They've developed cultural practices, technologies, and psychological strategies to cope with prolonged darkness. Artificial lighting, specific social gatherings, storytelling traditions that help maintain community bonds during the dark periods. When spring comes and the sun returns, it's celebrated. But the darkness is not seen as evil or wrong, just a seasonal reality to be managed. Similar adaptations exist in other cultures living at high latitudes. Scandinavia, northern Russia, Alaska, all have developed ways of living with extended darkness. Depression rates can be higher during dark periods, yes. But people adapt. They find ways to thrive despite the conditions. Space settlements will develop similar strategies. Artificial lighting that mimics natural day-night cycles. Social spaces designed to combat isolation. Cultural practices that celebrate the unique aspects of living in space. Perhaps holidays or traditions based on astronomical events. The alignment of planets, the passage through meteor streams, the anniversary of arriving at a new world. These would become meaningful in ways that Earth-based humans might not understand. Over generations, spaceborne humans might develop differently. Not genetically, necessarily, though that's possible over very long time periods. But culturally and psychologically. Children who grow up seeing black skies will perceive that as normal. They might find Earth's blue sky strange or even uncomfortable. Too much diffuse light, too much scattered illumination. They might prefer the clarity of space, where light sources are distinct and shadows are sharp. Studies of children growing up in unusual environments show remarkable adaptability. Children raised on submarines, on oil rigs, in remote research stations, all adapt to their surroundings and consider them normal. Spaceborne children will likely do the same. The darkness will just be how the sky looks. It won't carry the same emotional weight as it does for us. There might even be advantages to growing up in that environment. Greater appreciation for the cosmos, since you're seeing it without atmospheric interference. Understanding of scale and distance that comes from living in a place where the nearest neighbor might be millions of miles away. A culture that values self-sufficiency and careful resource management because mistakes in space are often fatal. These children might look at Earth and see it as fragile, vulnerable, too dependent on its atmosphere and biosphere. They might see space as the safer, more stable environment because it's predictable. It doesn't have weather, earthquakes, floods, or other natural disasters. It just has the consistent reality of vacuum, darkness, and the need for life support systems. Of course, there will be challenges. Some people will never adapt to space. They'll feel the isolation, the darkness, the separation from Earth too keenly. Return missions will be essential for mental health. People will need the option to go back to Earth if space proves too difficult. This might create a division in human culture. Earth-born who can't adapt to space. Space-born who can't adapt to Earth. Each seeing the other's environment as hostile or uncomfortable. Communication between these groups will be important. Understanding that different environments create different needs and perspectives. That there's no single right way to be human. That we can inhabit multiple environments while remaining connected through shared heritage and culture. Technology will help bridge this gap. Virtual reality might allow space-based humans to experience Earth without physically traveling there. Walking through forests, swimming in oceans, feeling rain, all simulated but realistic enough to provide psychological relief. Similarly, Earth-based humans might use VR to experience space, to understand what it's like to look out at the darkness from a habitat on Mars or an asteroid. These technologies could foster empathy between populations living in radically different environments. But there's no substitute for the real thing. The actual experience of darkness in space, of seeing Earth as a distant point of light, or not at all, of being surrounded by the void. That's something that can't be fully conveyed through simulation. You have to experience it to truly understand it. And that experience will shape who we become as a species. Will we remain primarily Earthbound, with only small populations in space? Or will we spread throughout the solar system and beyond, becoming a truly spacefaring civilization? The answer depends partly on how well we adapt to the darkness. If we can't overcome the psychological challenges, if the isolation and sensory deprivation prove too much, then space will remain a place we visit but don't inhabit permanently. But if we can adapt, if we can build habitats and cultures that thrive in the darkness, then the future might see millions or billions of humans living off Earth. The darkness won't be a barrier. It'll just be where we live. We, on Earth, are the unusual ones, living at the bottom of an atmosphere on a wet planet with a bright star nearby. Most of the universe isn't like this. Most of the universe is dark, empty, silent, and that's okay. That's how it should be. The darkness is not evil or threatening. It's just the universe being itself. Before we close, let's look at some specific historical moments when humans confronted the darkness of space directly. These stories help us understand what we're really talking about when we discuss space's darkness. The Apollo 8 mission in December 1968 was humanity's first journey to another world. 3 astronauts, Frank Borman, Jim Lovell, and William Anders, left Earth orbit and traveled to the Moon. On December 24th, they became the first humans to orbit another celestial body. And they became the first to experience the darkness of space away from Earth. As they passed behind the Moon, radio contact with Earth was lost. For approximately 45 minutes, they were completely alone. On the far side of the Moon, they couldn't see Earth. They couldn't communicate with anyone. They were farther from any other human being than anyone had ever been. Looking out their windows, they saw the lunar surface below, grey and cratered. And beyond it, the darkness of space. No Earth, no familiar reference points. Just the Moon beneath them and the void above. Jim Lovell later described looking out into that darkness and feeling profoundly alone. The sun was to one side, illuminating the lunar surface with harsh light and creating absolutely black shadows. But looking away from both the sun and the moon, he saw complete darkness. Stars were visible, tiny points of light, but they provided no sense of proximity or scale. They could be nearby or infinitely far away. There was no way to tell visually. The darkness wasn't just empty. It felt infinite. like he could fall into it forever and never reach anything. When they emerged from behind the moon and saw Earth rise above the lunar horizon, the sense of relief was enormous. That small blue and white sphere was home, was life, was everything familiar. Against the blackness of space, it stood out as the only spot of color in an otherwise monochrome universe. William Anders took the famous Earthrise photograph during this orbit. The image shows Earth rising above the moon's horizon, a half-illuminated sphere of blue and white against the absolute blackness of space. That photograph changed how humanity sees itself. It showed us how small and fragile Earth is, how alone we are in the darkness. The blue marble photograph, taken later by Apollo 17 in December 1972, had a similar impact. It showed Earth fully illuminated, a sphere of blue oceans, white clouds, and brown landmasses against the pure black of space. No other planets visible, no stars, just Earth floating alone in darkness. That image became an icon. It's been called the most reproduced photograph in history, and its power comes partly from the contrast. Earth, vibrant and alive and colorful, surrounded by absolute darkness. It makes our planet look simultaneously beautiful and vulnerable, like a jewel in a void, precious because it's the only one we have. The Apollo 13 mission in April 1970 provided another dramatic encounter with darkness. An explosion in an oxygen tank crippled the spacecraft, forcing the crew to abandon the command module and use the lunar module as a lifeboat. To conserve power for the critical systems needed to get home, they shut down almost everything else, including most of the lights. The spacecraft became cold and dark. The crew spent days in near darkness, conserving every watt of power. Looking out the windows, they saw the darkness of space, knowing they might die out there if the crippled spacecraft couldn't get them home. The psychological impact was significant. Being in a dark, cold spacecraft, uncertain if you'll survive, surrounded by the infinite darkness of space. It's hard to imagine a more isolating or terrifying experience. Commander Jim Lovell later wrote that looking out at the void during those uncertain days gave him a strange perspective. The darkness was indifferent to their survival. It didn't care whether they made it home or not. It would be there either way, unchanged, eternal. That indifference was somehow more unsettling than if the darkness had been actively hostile. At least an enemy can be fought. Indifference just is. But they made it home. The spacecraft's systems held together. Mission Control figured out how to navigate without the usual instruments. The crew splashed down safely in the Pacific Ocean, and they brought back stories of what it's like to truly feel the darkness surrounding you. To be reminded that space doesn't care about human drama or survival. It's just there, dark and vast and utterly indifferent to our existence. More recently, the Voyager missions have traveled farther into the darkness than any human-made object. Voyager 1 and Voyager 2 were launched in 1977 to explore the outer planets. They visited Jupiter, Saturn, Uranus, and Neptune, sending back the first close-up images of these worlds. These were revelations. Jupiter's great red spot, seen in detail, a storm system larger than Earth. Saturn's rings resolved into thousands of individual ringlets. Uranus's tilted rotation and blue-green methane atmosphere. Neptune's great dark spot and supersonic winds. Moons that turned out to be worlds in themselves. Io, with its active volcanoes. Europa, with its ice-covered ocean. Titan, with its thick atmosphere. Triton, with its nitrogen geysers. But their mission didn't end there. They continued traveling outward, into the region between stars. Voyager 1 crossed into interstellar space in August 2012. It's now more than 15 billion miles from Earth, over 160 times the distance from Earth to the Sun. Radio signals, traveling at light speed, take more than 22 hours to reach it. Out there, the Sun is just a bright star. Not the blazing disk we see from Earth, but a point of light. Still the brightest star in Voyager's sky, certainly, but reduced from a massive solar presence to a distant sparkle. Earth is completely invisible from that distance. Even Voyager's cameras, if they were still operational, couldn't distinguish Earth from the background stars. The spacecraft is traveling through interstellar space, the realm of true darkness. The space between star systems, where the density of matter drops to about 1 atom per cubic centimeter. If you were on Voyager 1, if you could somehow stand on its surface, you'd see the Sun as a very bright star, brighter than any other, but still just a point. Everything else would be darkness. Deep, absolute darkness, extending trillions of miles in every direction. The spacecraft itself is mostly dark now. Most of its systems have been shut down to conserve power. Its nuclear battery, powered by the radioactive decay of plutonium, is slowly decaying. The power output decreases by about 4 watts per year. In a few years, probably around 2025 to 2030, it won't have enough power to run any instruments. It'll go silent, continuing to drift through interstellar space in complete darkness forever. An artifact of human civilization traveling through the void. It carries the golden record, a phonograph record with sounds and images representing Earth and humanity. A message in a bottle cast into the cosmic ocean. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445. That's still an enormous distance. About 95 trillion miles. The star won't capture it. Its gravity won't significantly affect Voyager's trajectory. It'll just pass by, continuing its eternal journey through the darkness. No one will be there to see it. It'll be a dark, dead object passing through the dark space between stars. A monument to human curiosity and ambition, lost in the cosmic darkness. If an alien civilization ever finds it, they'll encounter an artifact from a species that reached out into the void. They'll see images of Earth, hear sounds of wind and water, and human voices. They'll know that somewhere in the darkness, a species existed that wondered if anyone else was out there. The New Horizons spacecraft, which flew past Pluto in July 2015, is now also traveling into the darkness beyond the planets. It's currently about 5 billion miles from Earth, roughly 52 times Earth's distance from the Sun. From New Horizons' perspective, the Sun provides only about 0.06% of the sunlight Earth receives. That's equivalent to about 300 times dimmer than a bright room on Earth. Still bright enough to see by, but a dim twilight rather than daylight. The spacecraft sent back the first close-up images of Pluto and its moon Charon. These images revealed worlds that had been mysteries for decades. Pluto turned out to have mountains of water ice, nitrogen glaciers, possible cryovolcanoes, and a complex atmosphere. Far more geologically active than anyone expected for a world so cold and distant. It also observed Arakoth, a small Kuiper Belt object, in January 2019. This was the most distant object ever explored by a spacecraft, about 4 billion miles from the Sun. Arakoth is a contact binary, two lobes touching each other, formed when two objects gently merged billions of years ago. It's a pristine remnant from the solar system's formation, unchanged for 4.6 billion years. These images showed worlds that spend their existence in the outer darkness of the solar system, barely touched by sunlight. Pluto's surface is illuminated by sunlight equivalent to a bright room light on Earth, but a bit dimmer. You could see, but not well. Colors would be muted. Shadows are deep and black because there's no atmosphere to scatter light into them. The sky, even at Pluto's noon, is black, filled with stars, but providing no ambient light. It's a twilight world, caught between the light of the sun and the darkness of deep space. And New Horizons is heading even farther out. Eventually, decades from now, it too will run out of power. It'll fall silent, becoming another dark artifact, drifting through the outer solar system and eventually interstellar space. Another human-made object, swallowed by the darkness. These missions show us that the darkness is real. It's not abstract or theoretical. It's something we've encountered directly, something our machines are traveling through right now. Every image from deep space, every measurement from distant probes, reinforces the same truth. Space is dark. Not sort of dark, not relatively dark. Absolutely dark in ways that earthbound humans never experience. And it's something we'll have to confront more and more as we push farther into space. The darkness is waiting for us. Not malevolently, but simply by existing. It's the default state of the universe. Light is the exception, the rare phenomenon that occurs near stars and in the brief aftermath of high-energy events. Everywhere else, darkness prevails. And as we venture out, we'll spend more and more time in that darkness, learning to survive in it, learning to navigate it, learning to make it home. The astronauts and cosmonauts who've traveled in space so far have been pioneers in this regard. They've taken the first steps into the cosmic dark and come back to tell us what it's like. Their experiences inform our planning for future missions. Their psychological responses help us understand what challenges lie ahead. Their courage in facing the void gives us hope that we can do it too. That humanity can expand beyond Earth, beyond the familiar light of our sun, into the greater darkness beyond. There's one more aspect of darkness we should consider before we conclude. The darkness within. Not the external darkness of space, but the darkness that comes from being cut off from sensory input. Isolation chambers, sometimes called flotation tanks or sensory deprivation tanks, create conditions of near-total darkness and silence. People float in body-temperature salt water in a lightless, soundproof chamber. The water supports your body so you don't feel gravity. The darkness is complete. The silence is profound. No light, no sound, no sense of touch except the water at exactly body temperature. Studies of people in these conditions show fascinating effects. At first, many people find it relaxing. Without external stimuli, the mind can rest. Stress decreases, muscles relax. But after longer periods, things change. The brain, starved for input, starts creating its own. Hallucinations are common. Visual hallucinations in complete darkness. Auditory hallucinations in complete silence. Your mind invents what's missing. Some people experience profound insights or creativity in this state. Without distractions, thoughts flow more freely. Problems that seemed intractable suddenly have solutions. Ideas that wouldn't have occurred in normal conditions emerge. Others experience anxiety or panic. The loss of external reference points can be destabilizing. You lose track of time. You're not sure if seconds or hours have passed. You lose your sense of your body's position in space. Without visual or tactile cues, proprioception becomes confused. These experiences in terrestrial isolation chambers give us hints about what prolonged exposure to space's darkness might do. Astronauts on long missions will have some sensory input, certainly. They'll see their crewmates, their spacecraft, their instruments. But looking out the window, they'll see darkness. Constant, unchanging darkness, broken only by distant stars. This could have psychological effects similar to sensory deprivation. The unchanging nature of the view might cause the brain to tune it out, to stop processing it as meaningful information. Or it might cause fixation, an inability to stop thinking about the void beyond the hull. We won't know until we try. Until we send people on missions lasting months or years with nothing but darkness outside. These will be psychological experiments as much as physical ones, testing human resilience in the face of the cosmic void. The selection of crew for such missions will be critical. Not everyone can handle prolonged isolation. Not everyone can cope with the knowledge that the nearest help is months or years away. Not everyone can look at darkness for extended periods without developing problems. Psychological screening will be essential. Candidates will be tested in isolation chambers, in confined spaces, in conditions that simulate the isolation of deep space. Their responses will determine whether they're suitable for the mission. Some people are naturally more resilient to isolation. They can maintain mental health even when cut off from normal social contact. They can entertain themselves, keep themselves occupied, find meaning in solitude. Others need constant stimulation, social interaction, variety in their environment. For them, a mission into the darkness would be torture. The challenge is identifying who's who before launching a multi-year mission. There's also the question of cultural differences. Some cultures emphasize individualism and self-reliance. People from these cultures might be better suited to isolation. Other cultures emphasize community and constant social connection. People from these cultures might struggle more with being cut off. International space missions need to consider these factors. A crew from diverse cultural backgrounds brings many advantages. Different perspectives, different skills, different ways of thinking. But it also means different responses to the darkness and isolation. Mission planners need to understand these differences and build crews that can support each other. Where one person's weakness exists, another's strength compensates. Where one person struggles with the darkness, another helps them through. These psychological and social dynamics will be as important as the technology that keeps them alive. You can have the best spacecraft, the best life support systems, the best navigation and propulsion. But if the crew breaks down psychologically, the mission fails. The darkness of space doesn't just challenge our technology. It challenges our humanity. our ability to cope with conditions we didn't evolve for, our capacity to remain sane and functional when everything in our environment tells us we should be afraid. This is why the exploration of space is as much about understanding ourselves as understanding the cosmos. Every mission teaches us something about human limits, about what we can endure, what we can adapt to, what breaks us. And each lesson helps us prepare for the next mission, the longer journey, the darker void. Some philosophers have argued that the darkness of space is a kind of mirror, that when we look into the void, we're also looking into ourselves, confronting our deepest fears, our sense of mortality, our place in the universe. The darkness shows us how small we are, how brief our lives are, how little we matter in cosmic terms. This can be crushing or liberating, depending on how you choose to interpret it. Crushing, if you see it as evidence that life is meaningless, that nothing matters. Liberating, if you see it as freedom from the weight of thinking, everything has to matter. If the universe is vast and indifferent, then we're free to create our own meaning, to decide what's important to us without worrying about cosmic significance. Existential philosophers like Jean-Paul Sartre and Albert Camus wrestled with similar ideas. The universe doesn't provide meaning. We have to create it ourselves. The darkness of space might be the ultimate expression of this. A void that we have to project meaning onto because it contains none inherently. For religious or spiritual people, the darkness might mean something different. Some see it as evidence of the need for something beyond the physical universe, a higher power or purpose that exists outside the material darkness. Others see the darkness as sacred, a reminder of mysteries beyond human understanding. Different interpretations, all valid ways of processing the same reality. The darkness is there, objective and real. What it means to you is personal. But whatever meaning you assign, the darkness remains. It doesn't change based on your beliefs or feelings. It just is. And we have to find ways to live with it, to function within it, to continue being human despite it. This might be the greatest challenge of space exploration. Not the technology, though that's difficult. Not the resources, though those are scarce. But the psychological and spiritual challenge of existing in a universe that's mostly dark, mostly empty, mostly indifferent to our presence. If we can meet that challenge, if we can maintain our humanity in the face of the void, then perhaps we're ready to become a spacefaring species, ready to leave our cradle and venture into the cosmic night, ready to make homes in the darkness and find light in our own communities and cultures. The universe won't provide that light. We'll have to bring it with us. And that might be the point. We're not exploring space to find light in the darkness. We're exploring space to bring light into the darkness, to create islands of warmth and life and consciousness in a cold, dark universe, to prove that even in the vast emptiness, meaning can exist, that even surrounded by the void, humanity can thrive, that the darkness doesn't have to win, because we refuse to let it. Let's conclude by reflecting on what we've learned tonight. Space is dark. Profoundly, absolutely, terrifyingly dark. The darkness you've experienced on Earth is nothing compared to the true darkness that exists between stars, between galaxies, in the vast cosmic voids. This darkness exists because space is mostly empty, because light only becomes visible when it interacts with something. because the universe is expanding and finite in age. The darkness is a fundamental property of reality, not a flaw or an absence, but a feature of how the universe is structured. It tells us about the nature of space, about the limits of light, about the scale of cosmic distances. It's a darkness that challenges human perception, that pushes the boundaries of what our senses evolved to handle. But it's also a darkness we're learning to understand, to measure, to navigate. Our spacecraft carry lights into the void. Our telescopes peer into the deepest darkness, detecting lights so faint it seems impossible. Our understanding grows with each mission, each observation, each new discovery. We're creatures of light, living on a bright planet under a warm star. But we're also capable of venturing into the darkness, of surviving there, of making it our home. The darkness of space is not a barrier. It's just the environment. And like all environments, we can learn to thrive in it. The future of humanity might be written in that darkness. Not on Earth, where we evolved, but out there, in the black void between worlds. Building new homes, creating new civilizations, spreading life and consciousness to places that have been dark since the universe began. If we do that, if we succeed in becoming a truly spacefaring species, we'll transform our relationship with darkness. It will no longer be something to fear, something to avoid. It will be home. The vast, dark ocean we travel through, the background against which we build our future. And maybe, someday, humans will look back at this moment, at us, at people who lived when Earth was all we knew, and they'll find it strange. Strange that we found space's darkness terrifying. Strange that we huddled on one small planet, afraid of the void. They'll have grown up in that darkness. It will be normal to them. Just as the ocean is normal to us now, even though our ancestors feared it, saw it as an impassable barrier, a realm of monsters and mystery. We conquered the ocean. We'll conquer the darkness too. Not by eliminating it, but by accepting it, understanding it, living within it. The darkness of space is terrifying only if we let it be, if we approach it with fear and ignorance. But if we approach it with knowledge, with preparation, with respect for what it is, the darkness becomes just another aspect of nature. Powerful, yes. Absolute, yes. But not evil. Not wrong. Just dark. And in that darkness, we'll find our future. Thank you for joining me on this journey into the darkness. If you found this exploration meaningful, please consider liking and subscribing. It helps this channel continue exploring the cosmos and sharing these discoveries with you. And remember, the darkness is not empty. It's full of possibility, full of unknowns waiting to be discovered, full of futures waiting to be written. The darkness is not the end. It's the beginning. Good night. And may you see the darkness not as something to fear, but as something to explore.